Start the recording now. 766, Nawaf. 766, Nawaf.
Yes.
Good. 289, Ali.
Yes.
Muhammad 323, excellent. 755, Abdulaziz. 755, okay. 941, Abdulaziz. Excellent. 323, Musa. Good. 012, Ahmed.
Yes, teacher.
012, excellent.
Yes.
033, Abdullah. Okay. 101, Mustafa. Okay. 117, Osama. Excellent. 895, Raid. That's good. 000, Karar. Karar. Okay, raising hands is good. 076, Muhammad. Okay. 290, Fahad. Excellent. 703, Rayan. Okay. And 123, Hamad. Excellent, guys. That's perfect attendance. So we will say everyone has attended period 1. Okay, we'll go back to the attendance later on. For now, let's go to our experiment. Again, the topic is rotational inertia. So the question is, what is rotational inertia? Well, before we define rotational inertia, let's go with the word inertia itself. I want to know if you take inertia in the theory class already. Anyone? Did you take this topic in theory? Hello? Shabab, did you take this topic in theory, inertia? Anyone? Not yet. Okay, good. It's fine. If you haven't taken it, then let me show you what's the meaning of inertia by showing several pictures, okay? First picture, this one. Do you see the image that I've shown you? This happens when you are driving, okay? When you are driving. And then suddenly, let's say that you're driving at 200, okay, 200 kilometers per hour, and the speed limit is 120, okay? So you hit the brakes, and when you hit the brakes, what happens? What do you feel in your body? This is the one which you see in the image, right? It's like something is, or there is a force that is pushing you forward. Do you feel this force? Anyone has experienced this one? Anyone has experienced this one? Oh, come on, guys. Can you hear me?
No, teacher.
Hello? You cannot hear me?
We can hear you, teacher.
Okay. Oh, yes, this is true also. When running over a big road bump or a hump, you suddenly hit the brake and you get pushed forward. That's why you have to wear a seatbelt, right? So this is the effect of inertia. So what happens there? Inertia is the tendency of an object, in this case the body, to continue its so-called state of motion. So what is the state of motion of the body? In this case, the man is driving in a straight line, and when you hit the brakes, your body as well is moving at the same speed as the car relative to outside, okay? And what happens is your body wants to continue moving forward because of inertia. And inertia in linear motion is affected by the mass of the object. Let me show you another image of an object where inertia is actually playing a big role, okay? And this one is actually quite interesting. You see there is a big truck, and inside the big truck there is a rock, okay? They use it to for construction. And what happens? the truck is moving at a certain speed, but suddenly the driver will apply the brake, and what happens? The object inside the truck, because it is not tied down properly, it will try to continue to move forward because of its inertia. And even if the truck is not moving at a very high speed, you will see that because of the big size of the object or the mass of the object, the object inside has a big inertia. That's because if a mass is bigger, okay, any mass, as long as you increase the mass, the inertia that it has also increases. So it will be more difficult to stop it, or if the motion of the object is zero, it will be more difficult to make it move forward. Imagine if you are trying to push a truck and trying to push a small car. Which one's easier to change the velocity? The small car. Why? Because it has a small mass, it will be easier to push forward. This is inertia in linear motion. Clear? The tendency of an object to maintain its state of motion, whether the state of motion is zero or not zero. Now, when we say rotational, rotational is, 1 second, I forgot to open one page. Okay. Rotational, that means the motion is in a circular motion, okay, like this. And this motion happens at a fixed axis. That means there is a point where the object rotates, okay? Well, I forgot to... There is one website that I'm supposed to open. Never mind. So anyhow, so what are the things that rotates? For example, the Earth, okay? It's a planet and it rotates on its axis. What else? The tires of your car, okay? The tires of your car rotates whenever you drive forward. What else? The steering wheel. When you control your car, the steering wheel, which the shape is usually circle, it rotates, among many things that rotate. If we combine the concept of inertia and rotational motion, we get rotational inertia. So rotational inertia is defined as the ability of an object to maintain its state of rotational motion. Okay? For example, I have here an image. There you go. Of a Ferris wheel. Okay? This is a ride which you see in many countries. For example, in London, we have the London Eye. In Dubai, we have Ain Dubai, which is the same thing, which means I Dubai. So this Ferris wheel has two major differences. Okay, let me clean up my drawing from my last class. Okay, what are the two differences of this Ferris wheel? Number one, the main difference is the radius of the Ferris wheel. Well, the similarity is both of them. Come on, where's my pen? Oh, there it is. Both of them will rotate in either direction, okay? But the main difference is that, number one, from the center of rotation, one Ferris wheel has a radius of, or a diameter of, you can say 135 meters divided by 2 to get the radius. The one from Dubai is bigger, okay? It has 210 meter diameter divided by 2 to get the radius. So that's the main difference. What else? The amount of people that it can carry is also different. So basically, the mass of the one from Dubai is bigger than the mass of the one from London. Okay? So those are the two main differences of our two Ferris wheels. Now, What's the question here? Because the two objects have different masses, the inertia, rotational, well, it's hard to write here. The rotational inertia of the two objects is affected by mass. Okay, so the inertia is affected by mass. Okay, because the one from Dubai is bigger in terms of mass, it has more inertia. Therefore, to make it rotate, the engine or the motor that requires to rotate it has to apply more force. Okay, what else? Because the motion is rotational, it is excuse me, it is also affected by the size, or in this case, by the radius of the object, the radius of the rotation. So unlike linear inertia, it's only affected by mass. If it is rotational inertia, it's affected by mass and by the radius. Okay? Now, before we continue with the experiment with inertia, we have to understand one thing. What causes rotation in the first place? Okay, what causes rotation in the first place? Now, rotation is caused by a force. That's why I wanted to open the website, but hola, let's just use a drawing. Rotation is caused by a force which is applied specifically to an object. Let me show you by making a drawing. Okay. 1 second. There you go. Okay. Assume that this is the tire of your car and you have, let's say, 4 bolts to hold it on your car like this. Okay. When you want to remove the tire of your car, because let's say it is flat, okay, what you do is you take a spanner or a wrench and you attach it to the bolts, and what do? You apply force, okay, so that you can loosen it. So the question is, where do you apply the bolts in order to unlock or to remove the tires of your car? Should you apply the force in point A, point B, or point C? Anyone? Shabab? No? In point A? So you take your hand and you push it here like this, force. It should be in point C. That's correct. Why do you have to apply it in point C? Because you want to rotate the handle, right? Now, when you apply the force, so it's not point B. Let's remove point B. Let's remove point C, point A. Let's apply the force in point C. What's the direction of the force? Will it be direction 1? Okay. Will it be direction 2? Okay. Or will it be, let's make this 3 and let's make this 2. So how do you apply the force, Shabab? In which direction should you apply the force? Should be in, Abdullah is correct. Musa Muhammad, that's correct. It should be in direction number 3, okay? So now, let us analyze the motion once we apply the force in direction of number 3, okay? So let's clean up our drawing. That's our wrench. I'm sorry because I'm using electronic pen and it's not easy to draw here. We apply the force in perpendicular. That means 90 degrees to achieve the best result at a certain distance from the center of axis, and this distance is D. Okay? And what happens is the wrench is going to rotate. In what direction? In this direction. And that type of motion is what we call rotational motion. You just repeat it and it will happen, and you will be able to remove each of your bolts, okay? Now, what do we call the force multiplied and applied perpendicular or 90 degrees to the distance d? This is what we call torque, okay? That is what we call torque. What does it mean, torque? Torque is a force that is applied 90 degrees multiplied to d, force that causes rotation. Clear? So torque is a force that causes rotation. Is that clear what it means, torque, Shabab? Is it clear what it means, torque? Come on, guys. I know it's afternoon, but you have to wake up. Have some coffee while having class. Okay, so torque is actually simple to understand. Just as long as you have force applied a certain distance from the axis of rotation, that force is called torque. Okay, it's a force that causes rotation. Now let's continue. What happens in our experiment today? Today, we are going to study the effect of a torque that is constant when we apply it on a rotating system. In our setup, in the lab, our torque will come from this. That's a hanging mass, okay? So the constant torque will come from the hanging mass. If you take mass multiplied by gravity, that's equal to weight. Clear? And we know that weight is a force. That weight is going to be applied on this string as a tension T. This pulley will change the direction of the tension. Therefore, the tension will go in this direction, T. Are you following, Shabab? I'm concerned that you are not listening. Are you following, guys? It's important for you to understand. Okay, good. Now, what happens to this string? This string is attached to a pulley inside here. On top of the rotary motion sensor, there is a pulley, okay? And I'm not sure if we have a picture of that at the top. Nope, not here. Maybe down here. Let me just check my pages. No, it's not here. Wallah, we need a better picture. Anyhow, there is a pulley under this device here, okay? So what happens is, let me erase this. This is the pulley, and the string is attached like this. And this string will pull the pulley, causing it to rotate, because the string is tied around the pulley, okay? Now what happens? This is the force that causes rotation. It is applied on the pulley at an angle of 90 degrees. Okay, it is applied on the pulley at an angle of 90 degrees. And what happens? We will measure the radius of the pulley. Therefore, force multiplied perpendicularly to the radius of the pulley will give us the torque that will cause rotation. Okay? So that's where the rotation is coming from. Now, let me just clean up. The rotating system that we are going to use are 3 different shapes. Why do we want to use 3 different shapes? We will study the effect of the torque to the different shapes. What are the shapes that we are going to consider? First, a solid disc. This one here. This is our solid disc. This one. Next, after the solid disc, we will also try to rotate a ring. Okay, what's the ring? this one. And finally, mass and rod system consists of two masses. Attached by a light rod. Okay, so we are going to try and rotate each of these three objects, and then we will determine. Yes, in the video we will show you how it works. Okay, and then we will determine the moment of inertia. I hope that you watched the video so you have some idea, but now I'm going to explain to you what's going on in that video. So how do we find the moment of inertia in each of the shapes? By experiment, the moment of inertia is simply equal to torque. What is torque? The force that's applied by this object, remember that? Multiplied by the radius of the pulley here, over angular acceleration, alpha. What is angular acceleration? It is the measure of angular velocity, how fast the object is spinning in radian per second, okay, divided by time. So the computer is going to measure alpha, angular acceleration. We are going to calculate torque, and by taking torque divided by alpha, we will be able to find the inertia of each object. That's what we are going to do today, okay? Now, before we do the experiment, we can find the inertia by theory, because for each shape, the inertia is actually calculable. You can take an equation to calculate the inertia. What are these equations? First, this is the inertia of the disk. The inertia of the disk is equal to 1/2 mass of the disk multiply radius of the disk squared. This one is the inertia of the ring. Okay, let me adjust this one to remove the number. There. So the inertia of the ring, because the ring has two radius, inside radius and outside radius, we have 1/2 mass of the ring multiplied radius inside squared plus radius outside squared. And finally, this is the inertia of the masses. And because the two masses are placed opposite of each other, you don't have 1/2. Okay? Instead, you have mass 1 multiplied distance 1 squared plus mass 2 multiplied distance 2 squared. How are we going to do our experiment? Okay, let's move forward, and let's go to the data sheet. Of course, all these things you can write it by reading your book, as I have showed you before. Okay, the first thing that you must understand is, how do we find the torque in the system? But this is by experiment, okay? So we have to measure first the diameter of the smart pulley. After that, we will change the value from centi to meter, and then divide by 2 to get the radius. Why radius? As I said, the inertia is equal to torque over alpha. And torque is equal to mass multiplied by gravity multiplied by radius. Anyway, let's continue. Also, you have to know how much is the applied mass that's causing rotation. What's the applied mass again? Let me go back to the picture. This one is the applied mass. This, the hanging mass, okay? So let's go to the video and review it and see how much are these values so that you can write them in your book, okay? Tell me if you cannot hear the video. Hello. We are going to study the rotational inertia of different shapes of objects. Let me fast forward. First, we are going to use the software 3 different shapes by applying a torque which will cause them to rotate, and the computer, with the help of the Data Studio software, is going to measure the angular velocity versus time, from which we can calculate the inertia of each object experimentally. The torque is calculated by taking the radius of this pulley Yalla, Shabab, that is the diameter of the pulley. We already measured it for you. Okay? Again, that's the diameter of the pulley. Where are you going to write it? You will go to the data sheet. Diameter of the pulley is there. Okay? Go ahead, write it. Let's continue. Okay? By which we apply a force which is equivalent to 25 grams. Okay, that's the applied mass, 25 grams. Where are you going to write it? Applied mass causing rotation, 25 grams. Of course, you have to change from gram to kilogram. Diameter has to change to meter, and then later on, from diameter, change it to radius. Is that clear, Shabab? I'll not put everything here, so you have some work to do. So let us continue. In order to calculate, wallah, I will just go to my OneNote. It's easier. There you go. Yes, Osama, you have a question?
Again, please, teacher. Radius.
Which one? Why you didn't listen? Come on. Let's go back. Last chance. Of this pulley, okay, by which we apply a force which is equivalent to 25 grams. Once our setup is ready, did you get it? Should I go back again? That's the diameter by which we apply a force which is equivalent to 25 grams. Once our setup is ready, got it? Osama?
Yes.
Okay, good. So once everything is measured for the torque, let's go to the disc. That's the first shape that we are going to calculate the inertia, okay? To calculate the inertia of the disc, you need this measurement. This is the rule. Mass of the disc and radius of the disc squared. So let us go and calculate or measure the mass of the disc and the radius of the disc, okay? Don't worry about the slope of the graph because this one actually goes here. So let's go to our video and find out the mass of the disc and the radius of the disc. Okay, that's the measurement of the disc. You can see the mass is on the screen, and you can see also the diameter of the disc is on the screen with the vernier caliper. Let's start with the mass. How much is the mass, Shabab? Anyone? 120 gram. And how do you change it to kilogram? How do you change it to kilogram? Divide by 1000 or times 10 raised to minus 3 or plus 3. It should be times 10 raised to minus 3. Okay, there you go. So now you have the mass. You will record the mass of the disc from gram and then change it to kilogram. Next question, how do we read the diameter of the disc? If you cannot read from here, on this video, I have the picture I took when I recorded this video, and this is the picture. It's the same thing, okay? Because in the picture we can zoom in. That's how we measure the diameter of the disc using a vernier caliper. Question, what's the diameter of this disc in centi? Anyone? 9.5? Good guess. Is it exactly 9.5? Anyone else? Anyone else? Come on, guys. 9? Okay. Anyone else? 9.53 from Musa. Mashallah, Musa is exactly correct. Okay? It's actually 9.53. Now, let us zoom in. How did Musa get the reading? Okay, because I want to review with you how to read from the vernier. Okay? First, when you read the vernier, let me take a screenshot of this figure here. And then we will work with the screenshot so I will not destroy my original photo. Okay, first, when we read, we always read from this line where you have 0. Is that clear? Not from this edge. This edge, voila, this is nothing. Clear? We always read from the line of 0 on the sliding scale. So always from this number. And then we read in centimeter. You have to check. At the top, this is inches. At the bottom, this is centimeter. Okay? cm here. So when we read, we know that this is 9. So we write 9 centi. Okay? But it's 0 here is not exactly 9 centi. It's 9.1, 9.2, 9.3, 9.4, 9.5. So we will write here 9.5 centi. However, if you look closely, where, let me put highlight, this line and the line of 0, are they straight? Shabab? Mustaqim? Tell me if they look straight for you. It's not, because if it looks straight, I will tell you to get glasses. If they are not straight, that means there is another number which you have to add here. Another decimal, not point, another number, okay? And how do you find the last digit? How did Musa find 9.53? Look at 1, Wahed. Mustaqim, it is not straight, so 1 is not in the picture. Look at 2, almost. Look at 3. If you look at 3, this line is perfectly straight. There. So the last digit is 3. Are we sure this is the only line that is straight? Yep. Look at 4, 5, 6, 7, 8, 9, even the 0 from here, which is 10. None of them is straight except 1. Only one number will always be straight. In this case, it's 3, so the last digit is 3, 9.53 centi. Okay, somebody will say, teacher, what about if 0 is straight? Simple, then it becomes 9.50. Is that clear, Shabab? Is that clear? Is it necessary to add a third number? Yes. Because in our standard, having 2 decimal here is always good for accuracy. It's always good for accuracy of the result. Clear? Yalla, Shabab, is that clear how to read the vernier? Okay, good. So that's how we read the diameter, 9.53. Where are we going to write it? In your data sheet, the mass is 120, diameter is 9.53. Okay? This is actually 120.10. Okay? So what to do? Change this to centi, from centi to meter, from gram to kilogram, and then take the diameter, divide it by 2 to get the radius in meter. Now, I will give you maybe 2-3 minutes. I want you to substitute the value here and then give me the answer. Yalla. Like I said, I will make you calculate. And if you do not calculate, we will stay here until 4:30. If I don't get an answer after 3 minutes, I will check the attendance. Go, calculate. Are you sleeping, Nawaf? Calculate this. This. Okay? Please focus, guys. Your internet is your responsibility. There's nothing I can do for that. Okay, Musa has an answer. Anyone else? That's strange. Raid and Nawaf have a different answer. Go ahead, calculate. You have 2 minutes remaining. Nawaf answer 1364. Are you sure? You must know how to calculate this, because for the next step, I will not give you the answer. I will just show you this sample now. Come on, guys. I have only 3 students. Nawaf, Musa, Raid, Abdullah. Only 4 students. What about the others? Is that copy-paste, Karar? You have to check. Is your mass kilogram? Is your radius meter? 1/2 mr squared. Come on, it's so simple. Wallah. What about the others? The others, they don't care. 30 seconds. Osama, this is the rule. Muhammad, he has 1.36 by 10 minus 4. Okay. And time's up. Let's calculate it together, okay? And let's see where is your mistake. First, the mass has to be in kilogram. So you have 120. Let's remove 0.10 if you want to keep it simple. 120 divided by 1,000. How much is that? 0.120. What else? Diameter is 9.53. Like I told you, Shabab, you should have calculator at home or in GIC lab. 9.53 divided by 2. Sorry, make it meter means divide by 100. It's 0.0953. Musa is correct. 0.0953. Divide that by 2 will give you 0.04765. Okay? Substitute the value. This is equal to 0.5. How do I get 0.5? 1/2 multiplied by the mass, 0.120, multiplied by, oh, don't forget the unit, that's kilogram, okay, multiplied by the radius, 0.04765, this is meter squared. What's the answer? Somebody got the answer, just one student. What's the answer, Shabab? Only one student replied with the correct answer so far. 1.36 by 10 raised to minus 4. If you will type it, you will type it like this. The Gasem, he got it correctly. 1.36 by 10 raised to minus 4. Okay, or asterisk is fine. So the inertia of the disk by theory is equal to 1.36 by 10 raised to minus 4, the unit kilogram meter squared. Is that clear, Shabab? That's how you calculate. Do not forget, change to kilogram, change to meter, make radius. In the equation, use square. Is that clear? Is that clear? Okay, now we know the inertia of our disk by theory. It's time to find the inertia by experiment. So let's move down to our data sheet, okay, and find the inertia by experiment. Before we do, let's watch how it's done in the video. So I'll fast forward, okay? First, you take the disk and you install it on top of the pulley. So this is the pulley I was talking about.
5 grams. Once our setup is ready, we will first start with the disk. Install the disk on top of the pulley, and with the help of a screw, tighten to make sure that the disk is not going to wobble or fall. Next, wind your pulley. Okay.
So you can see the string. The string goes around the pulley.
Make sure that the mass, which is going to apply with gravity the torque, is not swinging.
Okay, that's important. This mass should not be moving like this. It should not be swinging. If the mass is swinging, the applied mass, it's a source of error. What's the precaution? This mass should not be moving, or the applied mass should not be moving, okay?
It has to be steady. Secondly, the string. I don't know if you can see it from the video, but there is a string here, okay, right over here. Must be horizontal. It should not be going too high or too low.
Okay, the second part, the string should be horizontal. Let me explain to you what we mean. Where's my pen? If you look at the setup, okay, the pulley is here. The disk is on top of the pulley, okay? The string must be horizontal, passing through the second pulley and then going down with the mass that is 25 grams. This string here, let me use highlight so you will see it. This string, Hadi, must be horizontal, okay? Why should it be horizontal? Simple, because you want the torque, you want the forces being applied to be applied 100%. If the string is too high or if the string is too low, then you have to measure the angle with the horizontal, okay? But if the string is horizontal, however is this mass multiplied by gravity, it will be exactly the same force applied to make the torque. Is that clear? So the source of error, the string for the applied mass is not horizontal. Precaution, it must be horizontal. Okay? So let's go back to the video.
You can do that by adjusting this pulley here. This high, this is low, okay? But make sure that it is horizontal. And finally, you also set the pulley slightly angled to one side so that the string is tangent to your three-step pulley, which is on top of the rotational motion sensor, which is this one, okay? Click Start from the software.
That's the start button, you already know it.
Now, what you notice is that, let's stop first. In the graph is going down. What does that mean? That the direction of your rotation is going in the opposite. What you can do is you can take the rotary motion sensor, which is plugged to our interface, and reverse the polarity from there. Or you can take your pulley and angle it to the opposite side.
So what's going on? The graph is going down. So the problem here, your slope become negative. In order to make it positive, you want the graph to go up. So what to do? You reverse the rotation of the pulley, of the disc. That's the simple explanation, okay? So two ways to do it. You can switch the pulley to the opposite side, or you can get the plug for the rotary motion sensor and reverse the polarity. So let's continue.
Finally, you will wind the string again, this time in the opposite direction, to make sure that your graph is positive. This is what you do if the graph goes down instead of up. If you want to remove the data, just go to Data, and then No Data, or you can completely erase it. But be careful that you will not erase it all the data, okay? So just delete the last data run. Let's try it again. Click Start, and then Release. Okay, and then Stop.
So see, when we reverse the direction of the pulley, what happens? The graph goes positive. What to do with the graph is to find the linear fit. Now, you will not see some of the windows here, but we will see the result anyway.
Once you have your graph, we are interested in the straight line portion of the graph with a positive slope. You will highlight this graph, and just like before, you will click Fit and Linear Fit to get the slope of the graph. The slope is, of course, the first number. Once you finish, then...
Okay, question. What is the slope? Anyone? Can anyone tell me what's the slope? 37. You will go to your data sheet and you will go back to the reading, okay? And write the slope 37. That slope is alpha for the disk, angular acceleration of the disk. It goes in your equation here. Is that clear? Is that clear, Shabab? Is it clear? Come on, guys. Okay, good, good. What to do next in our Abdullah, Nawaf, which part? How to get the slope? Okay, let's go back to the video.
Linear fit to get...
Remember fit, linear fit, na? It will give you the slope of the graph which you highlight, huh? The straight line. So that slope there, can you see the small number here? Or if you want, let's go back. I made the screenshot. That's the slope here. Okay? What do you do with that slope? You write it in your data sheet. Where do you write the slope in your data sheet? Slope of the graph. There. Okay? That slope you will substitute in your equation here. Is that clear? The remaining part, to find the inertia by experiment, by doing the actual rotation, is to get the torque. Now, in theory, how we get the equation is given in the theory of your book. Let's go back to the theory. There. We know that torque is equal to inertia multiplied by alpha. How? Inertia is torque over alpha. Okay, and we also know that torque is equal to F multiplied by radius. I explained to you that a while ago. By combining these two equations, okay, we can get the inertia is equal to mgr over alpha minus mr squared. What is m here? Applied mass. What is g? Gravity. What is gravity? What is r? Radius of the pulley. It is given there, radius of the pulley. Okay, so let's go back to our data sheet and let's apply the calculations for our disk. Okay, disk. Oh wait, I'm using the note. Hina. Remember the values that we put in the beginning? The values for the torque. This values for the torque. Okay, remember the values we have? Do you have it, Shabab? The values for the torque. You have it, sir, in your book. You will take this and substitute it in our notepad. So let's go to our notepad and substitute it here. Okay. You know how much is the diameter of the smart pulley? Make sure that it's meter, not centi. From there, divide by 2 will give you the radius. Okay, and you know that the applied mass is 25 gram. Divide by 1000 will make kilogram. You will take these numbers and substitute it to this equation. Now tell me, what is the value of the inertia by experiment? I will give you, how much time do you want to calculate it? 2 minutes? How much time to calculate? I'll make it 3 minutes. Okay, go. And show me your answer, or you can type the answer. 90 seconds? That's 1.5. Yalla, calculate. How much is the inertia? The rule is given. Done? Two minutes left. Come on, guys. We're already 1 hour into our class. You got confused by what, Noaf? You can ask questions, of course. I'm still here. "45 seconds. 20 seconds. Two, one. Okay, time's up. What's the answer? What's the answer? Come on. Hello? I think it's time to check the attendance. Let's check the attendance another way. Let's see who is absent. Anyone who will not say present from our survey will be absent. I'll give you 3 minutes. Karar, can you hear, Karar? Of course, I will write how I answered, but you have to tell me how. Tell me your answer first. Abdulaziz got disconnected. Oh, he will get absent if it doesn't come back. So what's the answer, Shabab? What's your answer before I tell you my answer? You didn't understand, Abdullah? You will. Again, you have a value for the radius of the pulley. Sir? You have the radius of the pulley. That radius is R. What else? You have applied mass. That applied mass is M. You have slope. We know what is gravity, 9.8. What is the result when you calculate? Come on, guys. I will not simply give you the answer. You will not remember anything. I want you to experience how to calculate it. Yalla, give me your answer. No one was able to answer it? Not a single one? Okay. What is G? Gravity. Aren't you listening? Come on. Okay, let me substitute. But I will get the numbers from you. Okay, let me substitute, but I will get the numbers from you because I want to know that you are participating. Yalla, what's the diameter of the pulley? What's the diameter of the pulley, Shabab? 4.77. Thank you, Muhammad. 4.77 divided by 100 will be equal to 0.0477. What will be the equivalent radius? Anyone? Divide by 2. I told you this is very easy experiment, but if you will not participate, we will be here until 4:30. 0.02385. Read. Thank you very much. 0.02. Let me write properly. 0.0238. 0.02385 meters. The applied mass 25 gram divided by 1000, 0.123.025. Is that clear? How we get the measurement for the torque? Now let's substitute. Inertia of the disc is equal to mass applied. So 0. So Abdullah, he has an answer now. How long it take you to answer, Abdullah? It's fine. 0.025, the unit, kilogram. Multiplied by gravity, 9.8 meter per second squared. Multiplied by radius, 0.02385. What's the unit? Meter. Is that clear? Divide by the slope. It's a very long line. Okay, and what is the slope? 37 radians per second squared. 37 radian per second squared. Okay, let me move this because I need some space. How do I get space? There you go. Okay, there you go. Minus mr squared. What is m? Minus m, 0.025 kilograms squared multiplied by radius. 0.025 kilogram multiplied by radius, 0.0238 meter squared. That's how you calculate it. 1.57, 1.4, 1.58. So you have similar answers. So what is your answer finally? Let's calculate. By calculator, we can do it. 0.025 multiply 9.8 multiply 0.02385 over 37. That's the slope minus quantity 0.025 multiply 0.02385 squared. One second, I missed something in my calculator. There you go. Okay, I have an answer, 1.437. Okay, so my answer is, where's my pen? This is 5. My answer, I, inertia, experiment of the disc is equal to 1.44. I will round it off. 1.437, round off to 1.44 by 10 raised to minus 4 kilogram meter squared. Is that clear, Shabab, how we get this answer? So you can actually calculate carefully to get the answer. Just focus on the rule. What's the rule? Anyway, the rule is always given. This is the rule here. Okay, why you get 1.56? I wonder where you get 1.56. I have an idea. Why 1.56? Did you use 37? Did you use 0.2385? Did you use the exact numbers? Minus. Okay, you have to minus mr squared. Any questions, Shabab? Any questions how we get the inertia of the disc by experiment? Anyone? Is it clear? Okay. By the way, we have some issues with Blackboard because of all the online classes. Okay. So according to the email we received, we may need to upload some of the videos by YouTube. So I will give you update on this one, including our sessions. Anyway, we have two values for inertia. Okay. The first value we have by theory, Hadi. The second value we have by experiment, 1.44, by theory 1.36. What are you going to do? you have to calculate what we call the percentage error. Okay, let's start the percentage error with, voila, there's already an answer. I forgot to erase it. With the disk. Okay, so the percentage error for the disk, the rule remains the same. Fury minus experiment divided by Fury multiply 100%. So what is, whoop, you already saw the answer. I will just erase it, okay? And you can just calculate it again. What is the inertia by Fury for our disk? 1.36. The inertia by experiment? 1.44. We can remove times 10 minus 4 and the unit for the percentage error because they will just cancel, okay? So let's go back to the percentage error. Absolute value means the answer is always positive. So 1.36 minus 1.44 over 1.36 multiply 100%. What's the percentage error, Shabab? Yalla, go. What's the percentage error? Anyone? If you're listening or watching, you already see the answer. Anyone, Shabab? .88%. Anyone else? So you will write 5.88%. 5.882. Yes, 5.88 is more than enough. Any final answer, 2 decimal places, is more than enough. Is that clear, Shabab? Now we are finished with the disk. Khalas. Now the disk is finished. It's time to go to the ring. So this is the ring. It has inside radius. Okay, that's the inside radius here. And then it has outside radius because there is a hole in the center. What we do is the same thing. From the video, you will get the following data. Number 1, you will get the mass of the ring. You will get the inside diameter, change it to meter, mass must be in kilogram. Divide by 2, it becomes radius. You will get the outside diameter, change to meter, divide by 2, you will get outside radius. Again, the slope, you don't need it now, you need it for the experimental value. So first, I need you to calculate the inertia of the ring by Fury. Let us go to the video and give you the measurements of the ring. Okay, let me go back. Measurements of the ring. That's the disk, you already have it. Okay, this is the ring. Get the mass of the ring. And then I will open the image for the diameter of the ring. Alas, you have the mass of the ring? Please, don't ask me to come back later. You should participate now. Do you have the mass of the ring? Does everyone have the mass of the ring? .469.78. Done. Now let me open the folder. The diameter of the ring. This is the diameter of the ring. In order to read carefully, we will zoom in. You can see we use this side of the vernier to get inside diameter. Okay? Zoom in, and there. Now you can read the inside diameter of the ring. You want to know which one is mustaqim? Hadi, Khamsa. Number 5. That's the straight line. So how much is the diameter of the ring inside? Khalas, you have it? You can tell me, and then I can tell you if it's wrong or if it's correct. It's not exactly 5. It's not 5.5. Remember, you have to read from 0. But then the last digit is 5 here. 5.35. That's correct. 5.35 centi. Okay? Let me open the diameter of the ring outside. Diameter of the ring outside. Where is it? There you go. This is the diameter of the ring outside. Maximum zooming. Yalla, take your reading. When you are finished, tell me. You can type your reading and I will confirm with you if it's correct or not correct. 6.35? No, you're far from 6. This is 7. Read from 0. Come on, guys, you can do it. 7.65. 5, Mustaqim? Are you sure? 7.66. Yes. Hadi, look at 6. Straight. 5, almost straight. 7, almost straight. But 6 is exactly straight. Actually, if you want, you can even say 7.655. Okay? 7.655. But if you round it off, 7.66. Hadi. Okay? So the correct diameter outside, 7.66 centi. Kalas. Now, calculate the inertia of the ring by theory. Go. This one. Calculate this one. Substitute the value from the table and then calculate inertia of the ring by theory. After you calculate the inertia of the ring by theory, you can give me your answer. Alas, I forgot my timer. You get bonus time. What is D2? Diameter outside. We already calculated it, or we already measured it. So Muhammad, he has 1.63 by 10 raised to minus 3. Anyone else? Anyone else want to copy his answer? Shabab, anyone else? Come on, guys. Calculate, calculate. Abdullah, we already gave D2. You missed it? Oh, come on. That's D2. Diameter outside. Muhammad already gave you. 40 seconds. (5.12 by 10 minus 4). Wow, Musa's answer is different. D1 is 7.66. Nope, that's D2. D1 is 5 point something, if I remember. That's it, time's up. Okay, we have two different answers. 5.126 by 10 minus 4. And what's the other one? 1.63 by 10 minus 3. Let's calculate. So first, 1/2 is the same as 0.5 multiply. What's the mass of the disk? We have it in the chat. 469.7. Divide by 1,000 to make it kilogram. 0.4697. Okay? Okay. 46978 to make it complete. Multiply by what is radius 1? 5 point. Remember the inner diameter? 5 point. Anyone who remember? 5.35. Right? Musa was correct, remember? 5.35. But this is in centi. To change it to meter, divide by 100. So 0.0535. And then divide by 2. And then divide by 2. Anyone who got this answer? Okay. So it becomes 0. Because it is radius, not diameter, 0.02675 square plus outside diameter is 7.66. So 7.66 divide by 100, 0.0766 divide by 2, right? 0.0766 divide by 2, 0.0383, 0.0383, and then you will square it, right? Plus, you will add this 2, so this is squared. That's R1 squared plus R2 squared. Did you get how to calculate, Shabab? Now I will calculate the whole equation. 46978 by 0.5. So what's your answer? Right? Nope, that's too far. What's your answer? Hamad, 1.63? Or Musa is correct? Which one is correct? 5.12? Now you get the idea, Shabab, how to calculate it? So your answer is 5.12 by 10 raised to minus 4. Okay, let's take your answer. Maybe it's correct, maybe it's not. Let's take it. 5.12 by 10 raised to minus 4 kilogram meters squared. Now, in order to calculate the inertia by experiment, we will take the slope and then we will divide torque over slope, alpha. Okay? Or simply, we will use the same value for mass. Which mass are we talking about? Applied mass, 25 gram. Okay? Which G? Gravity. Which radius? Radius of the pulley. The same number that we use for the disc. What numbers did we use for the disc? This one. This is the radius of the pulley, and this is the applied mass. And gravity is, of course, 9.8. Clear? The only value we will replace in the equation is the slope, alpha. So how do we take the slope? We go back to the video. We forward, okay? Forward to the ring. Ring, 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 there. Now, because the ring has a hole in the middle, we put it on top of the disc. Is that clear? So watch the video here and see how we find the slope of the ring.
You will notice that at the top of the disc, there are two holes, this one and this one here. On your ring, there are two bumps. You have to align them, make sure that each bump will go inside the hole of the ring, of the disc, sorry. And from there, the ring can be rotated and the rotation will be more stable because they are attached together. Again, you can wind the string around the pulley, hold it in place. You can hide the original data from the ring by going Data, No Data, and finally click Start and Release. There you go. Make sure that you click Stop once the graph starts to go down. Again, we are interested in the straight line portion of the graph. Select that line, go with Fit, Linear Fit, and you have the second slope. That is the slope of the inertia.
Okay. You see the slope, Shabab? 8.57. 8.57. Okay, done? Let's minimize this one. And let's go to our slope for our ring. Write the slope here, 8.57. Okay, you will use that slope, substitute it here. Now I want to explain to you one thing. Why does it say R plus D? Do you have to take the slope of the disc and add it to the number 8.57? No. What you will do is actually just use 8.57 because look here, okay, that is the slope of R plus D here. It's just the slope of the ring and the disc together because when we made the rotation for the ring, it has the disc with it. So it's the total angular acceleration of the two objects together, disc plus ring. That's the meaning of R plus D, ring plus disc, okay? So what do? Simple, just calculate this value using this rule, okay? And give me the inertia of the ring and disc together by experiment. Yalla. Calculate, please. You have the values of the ring, inside diameter, outside diameter. You don't need all this. You need only the slope. Okay? You have the values of the torque, the smart pulley or the pulley diameter, radius, the pulley the applied mass. You have it. Just substitute the value. Why is it supposed to be in the minus? Why do you say that, Muhammad? Just substitute your values and find the inertia by experiment. Go ahead. Don't worry about the disk and the ring together. There is a step after this one. Just calculate the inertia first. No, it's not going to be in the minus. Which R you will take? 1 or 2? La, none of them. You are losing again. Shabab, the measurement of the inertia of the ring, let me show you. Let me make a rectangle. This measurement, diameter, radius, mass, this one is for this. The slope is for this. What about mr squared? You will use this because it's from the torque. Clear? So which m are you going to use? Applied mass. Which g? Gravity. Which r? Radius of the pulley. Okay? Now calculate. Come on, guys. You can do it. Should be very easy. Done? What's the inertia? 6.68 by 10 minus 4. Okay. Muhammad again, the first one. Anyone else? Come on. What about the others? Two minutes more? Sure. I'll give you 3 minutes if you like. This is your time. $5.39. Okay, that's a big difference. Anyone else? Anyone else have the same or different answer? Come on. Now remember, by theory is 5.12. Okay. So let's see which answer is the best one? Yalla, Shabab. I'm still waiting for an answer. One minute. I'll be back. If you are going out, by the way, just please tell me, okay, so that I know. Leave a message. Muhammad, I don't exactly know what I'm doing wrong. Why? 0. Which calculator are you using, Abdullah? Are you using your mobile phone? Okay, let's do this. First, like I said, to calculate the inertia by experiment, we will use the value that is this. Okay, the only thing that we will change is the slope. So this will remain 0.2385 and 0.025. So let's go to the ring. Okay, we know that the radius is 0.02385. We know that the mass applied 0.025, and this is kilogram and this is meter. So substitute 0.025, that's the mass, multiplied by gravity 9.8, multiplied by the radius 0.02385. Divide by the slope. What's the slope again? 8.57. 8.57. There is the slope. Okay. What's the next step? Minus mr squared. What is m? 0.025. What is r? 0.02385 squared. You got it after I write it or what? So what's the answer here, Shabab? Tell me. Which one is correct? 5.39, 6.68 by 10 raised to minus 4. Okay. Let's say 6.68 by 10 raised to minus 4 kilogram meter squared. The problem is, look, according to the theory, it's only supposed to be 5.12. So why is there a big difference? Because this is the inertia of ring plus disk together. That's what it means, inertia R plus D. Why do we have the value ring plus disk together? Because the ring and the disk were together during rotation. How did you get 5.39, Musa? Maybe you get one step ahead. Okay, let's see. In order to find the inertia of the ring alone, because this is only for the ring by theory, okay, by experiment, then you have to minus the inertia of the disk using this rule. The inertia of the ring alone is the inertia that we calculated, Hadi, minus the inertia of the disk alone. So you will take 6.68 by 10 raised to minus 4. What's the inertia of the disk? Go back to the disk, also times 10 minus 4, we will minus 1.44 because that's the inertia of the disk by experiment. Okay, so go back to the ring, minus 1.44, and we know that this is times 10 raised to minus 4 kilogram meter squared. So what's the answer here? Anyone? 6.68 minus 1.44, 5 point? Anyone? 5.24 by 10 raised to the minus 4 kilogram meters squared. Any questions, Shabab? This is now the inertia of the ring by experiment. Is that clear? It's time to check the attendance because some of you might be sleeping because nobody answered my question. Let me see if I get the SMS 9354. Yalla Shabab, you know how it goes with the attendance. I will call your name and you will reply in any way that is convenient for you. 766, Nawaf. Okay. 289, Ali. 289, Ali. Where did Ali go? 289, Ali. Absent. 323, Muhammad. 323, Muhammad. Okay. 755, Abdullah Aziz. Okay. 941, Abdullah Aziz. 941, Abdullah Aziz. 23, Musa. 012, Ahmed.
Yes, teacher.
Excellent. Abdullah, 033. 101, Mustafa. 117, Osama. 895, Raid. 895. Okay. Karar, 000. Excellent. Muhammad, 076. Fahad, 290. Rayan, 703. Hamad, 123. Last chance, Ali Al Mutawa, 289.
Yes, I am here.
I told you, before you go to the bathroom, leave a message. Or if you want to go drink water, whatever it is. So you don't
Sir.
get absent. Okay. That's it, guys. Last shape. Okay? Last shape. The ring, you have to make percentage error. I already showed you how to do it. Theory minus experiment, divide by theory, multiply 100%. The last shape is mass and rod. Mass and rod. Again, let me repeat so you don't get confused. This measurement of the mass and the distance, what distance? Distance 1 and distance 2. This measurement is for the theory calculation. The slope is for the experiment calculation. mgr minus mr squared here will come from the torque, not from the measurement of the mass. Clear? I will not calculate anymore. You have to do some calculation for your own report. I will just show you the reading. So let's go to the video and get the reading of the masses. This is the reading for the mass and rod system. Go ahead and record it in your system. Okay, take the reading and record it in your system. And I will come back in a few minutes. Okay, guys, done? You have D1, D2. How much is, sorry, mass 1, mass 2. How much is D1? Can you tell me how much is D1? Not 17. Up to this point here. I put the mouse here, 18 centi. Okay, how much is D2? D1 and D2 equal 18 centi. Is that clear? 18 centi. Okay. Once you have D1 and D2, you have to, and M1 and M2, you have to calculate this. From there, you will find the inertia, and then you will find the slope from the experiment. So let's go and find the slope for our mass and rod. Okay, watch this.
And once that is done, you may now install it on top of your rotary motion sensor. Just make sure that your masses are exactly at the end, here, okay, here, and here, at the end of your rod. Next, wind the string around the pulley. Okay, you can do like this. Hold the mass in place. Make sure that the hanging mass is not, this one here, is not swinging. Let's hide the data from the previous run. Click Start and Release. And stop. Now, make sure that when you're doing the experiment, you try to not bring your face very close to the rotating object so that you don't get injured. Once that is done, again, we select the positive slope of the line, the straight line portion. Go to Fit, Linear Fit, and that's your third slope. You can now calculate the inertia of the...
Okay, so that's the slope, 1.09. And yes, D1 and D2 are both 18 centi. So let's go back to our data sheet. You have D1, D2, M1, M2. Make sure, Shabab, everything in kilogram and meter. Okay, this is 1.09. Now you can calculate both the inertia of the masses by theory and the inertia of the masses by experiment. Once you have calculated both, what to do? You will find the percentage error. Okay, for the masses, you will find the percentage error for the masses. For the masses, you will notice that the percentage error will be a little bit higher. Okay, but it's okay. Next, once you finish all the calculations and all the percentage error, you have to finish your report. When you finish your report, go back to the video. I already sent you the link in your GC. Okay, yes, yes. Don't get smacked in the face with the rod. We will discuss source of error. So again, go back to your to the video which I sent you, to the link, and take a screenshot like this. Okay, this video. See how I will combine all three graphs in one graph.
What you can do is go to Data, select the first run, Fit, and then Linear Fit. Again, go to Data, select the second run, and go to Fit, Linear Fit. Once you have all three, just arrange the slope.
Okay, so that's how you combine them in one graph, so you don't need to print if you have to print, or you need to make PDF. Just one page with the 3 line is good enough. Take a screenshot of this. I use the snipping tool. This is the snipping tool, okay? Take a screenshot like this without my face, and that's enough to submit the report, okay? It shows the 3 slopes. Attach it in your report as PDF. Finally, source of error and precaution. Now, the sources of error and precaution, I already gave you one in the beginning. No, I gave you 2 sources of error and precaution. Can anyone tell me? You can do that by microphone. If you don't want to type it, you can do it by microphone. What's the source of error precaution which I gave you in the beginning? Anyone? You haven't caught it? Then you have to watch the video again. Yalla Shabab, I gave you source of error and precaution in the beginning. You didn't catch it? Sorry, that means you have to review. There are some precautions in the book, okay? This one. But it's not stated properly. Maybe the grammar is wrong or something, okay? But some of them are okay. This one is not necessary, not useful. This one is, let me fix it. The thread for applying torque must be tangent, not to the rotary motion sensor, but to the, just say, must be tangent to the pulley, okay? What else? The slope must be positive. Yes, that's correct. Take the maximum point in the line to linear fit. Yeah, but this is not necessarily correct. I told you something about this mass. Should not be swinging. That's the precaution, okay? What else is a source of error in this experiment? I told you something about this string. It should be horizontal. That's the precaution. What else? What else is a source of error? Anyone? Okay, I'll discuss with you source of error. Remember I told you before in one of our experiments, if an experiment is electrical, there is always internal resistance. If our experiment is mechanical motion, there is always friction. Okay? A source of error is always friction. Precaution, we can always reduce friction. Whoa, where did my typing go? Precaution, reduce friction. So now you have 3 sources of error and 3 precautions. What else? There is still another source of error. You can say that the shape is not, you can use the term perfect or you can use the term balanced. The shape is not perfect or balanced. Okay? Capacitance, no, we are not discussing capacitance now. What's the precaution? Make sure the shape is balanced. Why is that? Why is the shape to do rotational inertia must be balanced? Let me show you in the video, okay? Remember our masses and rod? Look at the value for the masses. I want to show you the value for the masses. Mass 1 and mass 2, are they balanced? Are they equal? Anyone? Nobody has microphone in this class? Come on. Mass 1 and mass 2, are they equal? They are close, but they are not equal. Not perfectly equal. What's the effect when you rotate a system that is not balanced? Let me show you an example in real life of rotation where we need balance. It will wobble. Exactly. You see this image? What is this image here? This is the image of what? When you buy a new tires for your car, they test it by rotation. Sa? Yes or no? When they test it by rotation, they'll put it in the machine will rotate it, and the machine is going to measure the balance of the tire. What do we mean by balance? The weight or the mass at this end must be equal to the weight or the mass in the opposite side of the tire. If one side is more heavy by, let's say for example, where's my pointer? Let's say that this is heavy by 5 grams. The technician will take 5 grams of mass from here and attach it in the opposite side, plus 5 grams to make it balanced. Because if the rotation is not balanced, what's going to happen? This tire will vibrate or wobble, okay? So a rotation which is not balanced will actually affect the motion of the rotation. What else? The engine of your car. Inside the engine of your car, you have your pistons moving in different direction. Okay? And it's attached to the crankshaft. And look, it's rotating. But the problem is it's not perfectly balanced. That's why the engine, when it's running, it's vibrating. But the technician, using the computer and the timing, will try to balance the engine, okay, so that the vibration will be minimal. The more expensive the engine, the more balanced it is when it's working, like the engines that they use for racing, the Formula 1 racing, okay? What else? Electric cars do not use this type of engine. They use electric motors. And the rotation of electric motors is more balanced. That's why they are more efficient than the petrol engines, okay? What else? For balanced rotation, in our experiment, if you look at the graph of the third one, masses and rod, okay. If you look at the graph for the masses and rod, let me increase the size, okay. You will see that in our graph alone, there is also vibration in the rotation. Where do you see it? Let me put a circle. No, this one is not clear. Let me go with the combined graph. Here, it's more clear here. If you look at the line, it's not perfectly straight. Look at this area. You can see that the dots will go up and down from the straight line. Look at this area. You can see the dots are not perfectly straight. What does this mean? This means that the vibration is not balanced. Is that clear, Shabab? The vibration is not balanced. That's the source of error, which I'm explaining to you. Where is it? Where is it? Here. Source of error, precaution. The vibration is not balanced. So if you make the shape balanced, that's a good precaution. That's our experiment, Shabab. I will open the Blackboard for you to submit the PDF report. Make sure it's PDF. Make sure it's less than 5 MB, or you might face problem with submitting the report. Any questions? I see that some people already left. Maybe I should check the attendance again. Any questions, Shabab? Do you have to answer these questions? Yes, you have to answer these questions at the end. Okay, that's it. I'm stopping the recording. And